Yeah, please go ahead.
Okay. So, good morning. Hi, everyone. Um, Thank you, Vadim, for making this workshop and orchestrated it so nicely. So I think my presentation will be will complement Jürgen's one, which had a beautiful introduction to radar. So what I'm going to talk about is automotive imaging radar for autonomous driving. I will talk what Mobileye is called drive-by radar and the challenges that we have and how imaging radar really fits into the autonomous driving picture. Just as an example, you can see here in this video, I think it is in Jerusalem. So you can see that the urban scene, for instance, is very, very dense, very complex, lots of different types of objects, many reflectors to radio wave. This is where the imaging radar has to deliver a good sensing. I will stop it now, I guess. Before I start talking really on radar, I would like to give you the broader picture of Mobileye strategy and how true imaging radar is embedded in it. So what you see here is kind of three families of products. We have here the supervision, the chauffeur, and drive. On the lower bar, you can see the level of autonomy. So on the left side is basically ADAS, and on the right side is kind of autonomous driving. The bar that reads drivers is for what is called consumer AVs, as a vehicle that people purchase and use. And the rightmost column is robotaxi, is the service. We believe that in consumer EV, still there should be, at least in the recent future, a driver for the rare occasion that the driver needs to intervene. And in robotaxi, there will be teleoperations because there are also issues beyond the drive itself, behavior issues, social issues, and so on and so forth. Now, if you look on above these two bars, you can see the scalability of the architecture in terms of the SoC. So you can see the part number, which is IQ6 now. This is the current generation of Mobileye SoC. Each IQ6 has 30-something tera operations per second of deep learning. You can see how the name convention goes. So it has the two letters of the product family, and then the IQ type, and then number of SoCs. And you can see that as the driving scenario is being more complex and more demanding from highway to urban, then the system scale up both in compute capacity, has more IQ chip in it, and also in the sensing suite. And as you can see in Mobileye strategy, imaging radar are essential part for the eyes of hands-off, which is the autonomous driving, for rural, arterial, and urban environments. True redundancy is is another concept of Mobileye, where we look on multimodality sensing in two different ways, if you like, or the multimodality serves two purposes. The first purpose is really the difference between a camera, visible light, and a radar. Automotive radar wavelength is around 4 millimeter in the band of 76 to 81 or 76 to 77 gigahertz. So it's a bit less than 4 millimeter. And visible light is in the order of micrometer. So there is a 3 order of magnitude difference that generate these differences in the sensor behavior. Also, the camera and radar complement each other very nicely. For instance, camera is a passive sensor, and radar is an active sensor. So camera has issues with the low lighting condition, and radar doesn't care about the lighting condition. Camera is very good in semantics, in angular resolution. As you learned also in Drogan talk, radar has an issue of spatial resolution. Radar can natively measure the distance and the Doppler. A simple camera usually can't do that, so on and so forth. So this is one aspect of multimodality sensing. But there is another aspect, which is very important to Mobileye strategy. And this is that if we look on a camera alone subsystem and a second subsystem of radar and lidar or radar alone, we have two independent sensing systems. And if we have two independent systems, we can to generate the overall probability of failure to use the multiplication of these two subsystems. So let's say that you know, every one of us would like to drive a car that has been tested, or the system in it has been tested for like 10 to the 7 or 10 million hours in real world driving. So assume you need to you make a small software change, and now you have to run you know, testing operation for 10 million hours. It doesn't make sense. But if you take for instance a primary system that is independent of the secondary system, so you can just multiply the probabilities, and actually you can, for instance, test the primary system for 10,000 hours and the secondary system of 1,000 hours, which is very practical and affordable, and voila. You get the amount of you know, failure probability that you would like to achieve with a practical and affordable way. So you can see this in the right side of the slide. So you see that both there is a difference kind of between convenient or comfort sensing and safety sensing. So you see that there is true redundancy in the safety sensing, where the system generates a different world model, one based on the camera and the other based on the radar. And then these two world models, you know, independently raise flag to the policy, and the policy can then make an emergency maneuver or emergency brake or prevent an accident. In parallel to this, as long as there is no critical safety issue, there is a fusion between the camera and the radar, and this fusion creates a combined world model, and the vehicle is controlled based on the combined world model. Okay, so there are two aspects of true redundancy. One is the multimodality, the complementarity of the sensor, and the other is the validation and the safety architecture. Now, but there is another kind of trick here, or hidden assumption. The assumption is that the world model can be generated based on radar alone. And this is what we call drive by radar. It means that we can create a world model that is good for driving, for autonomous driving, based on radar alone. So in our radar design, and the reason that Mobileye established a radar product and development is because there were no radars on the market that were good for drive by radar, that you could drive your car. Of course, the radar cannot detect the signals and so on and so forth. So semantics has to come from map, so on and so forth. But other than that, the drivable space estimation and all the control of the car has to be based on a radar only, and not on a fusion between radar and another sensor. Of course, there is a variant of it. You can add another layer of front lidar to get more data and more accuracy into the secondary subsystem, and this is the Mobileye architecture. I want briefly to help you with acronyms to people that are not familiar with Mobileye or with automotive radar. So ADAV is autonomous driving of vehicle. IQ is the Mobileye autonomous driving SoC. ODD is the driving scenario domain. RSS is the code name of the safety control logic of Mobileye. RAM is the crowdsourced mapping of Mobileye that really collects not just the static data, but also behavioral, the driver's behavioral data. DXP is the Mobileye solution architecture that consists of objective, non-customizable part and customizable part. BSR is our code name for the radar, and for the corner radars, which are smaller radar, we have BSR corner, BSR-C. SLL is side lobe level. It's a physical result of the modulation being finite, actually in 4D, so finite in frequency, finite in time, and finite, the aperture is finite in space. And this this practical fact create side lobes. Bandwidth used also for frequency and throughput. Teraops is the compute capacity, field of view, of course. We call the PDNFA the probability of detection and probability of false alarm. Both are very important because also false alarm is very important because if there are too many false alarms, the car will make false emergency braking or emergency maneuver just because of the false alarm, which is very, very unacceptable. SRR, MRR, LRR are the acronyms of short, medium, and long-range radar, and RCS is radar cross-section, is the discovering the amount of energy reflected from an object towards the radar. Okay. So this picture actually is similar to the video I showed you in the beginning. So you see here a very complex scene with the motorcycle between the cars. Each object here load the scene, make the sensor life harder, if you like. There's a very good resolution that is required, but also the ability to handle multipass, because every car here and building is also a reflector, like a mirror. And also high dynamic range, because as you see, the motorcyclist has a much lower RCS than the bus. For instance, it could be 20 or even more, 25 dB difference between the two, and sometimes a large object like the bus can overwhelm the sensor, and it would not detect the motorcycle. On the bottom, you can see other kind of scenarios. So you see that it's funny because radar has conflicting requirements. For instance, for parking, we need to detect the vicinity of the car, even up to the body itself. But for highway, we need to detect for cargo or a motorcycle or pedestrian from 200 and 300 meters. We need the sensor to be accurate. We need the point cloud to be dense. And so you can see there are many requirements for a true imaging radar. I want to talk about think that it's practical, but not just practical. I think it's behind some of the topics that Jürgen even touched on, which is what I call here the aperture challenge. So the radar output is usually consists of 4 dimensions. We measure or estimate range, Doppler, azimuth, and elevation to each reflecting object in the field of view. Now, the resolution in each dimension is affected by different factors. For instance, for spatial resolution, the aperture physical size sets the native resolution in a simple formula. That you can see here, it's the wavelength divided by the aperture length. This is, of course, for 1D, but applicable for 2D. And if you can see for 4 millimeter and 10 centimeter radar, which makes sense, we can get down to 2 degrees. I will not describe in this talk what is MIMO radar, but believe me, many MIMO radar use this trick, and actually we can get in MIMO radar a virtual aperture, what is called, which is double the physical length. So we can get down to 1 degree resolution in azimuth for a 10 centimeter wide unit. Usually people invest more kind of antenna elements in the azimuth than in the elevation, and you will see that the elevation has a poorer resolution, let's say 2 degrees in this case. In terms of the RF bandwidth, although automotive radar is regulated for 76 to 81 gigahertz, a global regulation is only between 76 to 77. For instance, one example in China, it's regulated only until 79, for instance. but the common kind of regulation requirements are only in 76 to 77. Hence, many car OEMs stick with this band of 76 to 77, and this limits the bandwidth of the radar to be 1 gigahertz. And sometimes from practical and interference reason, you want to be less than that. So let's say a quarter of that, so 250 megahertz. And the resolution is related to the speed of light and the RF bandwidth of the modulation, and it gets you down in 1 gigahertz to 15 centimeter, and in 250 megahertz to 60 centimeter. And usually, if windows are implemented, it's even worse than that. So Doppler is a frequency kind of estimation, and as such, it has an inverse relation to time. And Doppler resolution is determined by the frame length. So here you can see an example that give like 0.2 meter per second in radial velocity estimation. So it could be that the 10 millisecond frame makes sense, but if you look on the sensor frame rate, which is typically, let's say, 20 frames per second, then the amount of time that's available to transmitting and processing is less than 50 milliseconds. So we can not get much better than this one without super resolution or other tricks. So this is the resolution kind of that is common or typical to radar. Now, if we look on the resolution and the field of view, so we want the finest resolution we can achieve and the larger field of view, of course, because otherwise we have to stick more units or we are limited in our sensing capacity. So here is a kind of typical simple example, let's say. So for range resolution, let's say 0.5 meter and maximum range of 350 meter, Doppler resolution, as we said, 0.2 meter per second, and that span 100 meter per second, and azimuth, let's say, on 140 degrees in 1 degree resolution, and elevation in 60 plus minus 30 in 2 degrees. So if we multiply everything together, we get a very, very large number. And if you look on computation complexity, so it's somewhere between FFT complexity, which is n log n, and super resolution complexity, which is n to the 3. Indeed, there is some sparsity that can be leveraged in many ways, but it's an overwhelming figure of in terms of grid, and each grid is a hypothesis, and you have to estimate whether there is an object or not in this grid space. So it's really a huge task, and really what's dictates the vendor kind of strategy is this complexity. So you can see many different solution and strategies, but this is the source of the problem, okay? Because we need to deliver large range of value in high resolution, and this the result is huge. What are the kind of two common solutions? Also, I think Jürgen touched on that a bit. So one solution is sparsity and trade-off. So the idea is try to reduce hardware to the minimum, but still maintaining a high performance spec, high resolution, large distance, so on and so forth. The problem is that, as you saw in the in the video in the beginning and the image a few slides back, spec does not reflect real life use cases, because it's all about the long tail, and not about a spec that you can measure between two corner reflectors. Okay, and real life challenge the radar from many different aspects, like point cloud density, link budget, field of view, false alarm issues, so on and so on. I want to give you an example for this kind of trade-off, and it most, I think, striking and visibly effective in the array example. So if you look on sparse array, meaning the distance between antenna element is not half a wavelength, or a multi-static radar, meaning radar that has a hole, there is a missing antenna elements between them. So there's no free lunch. This topology has issues. The main issue is ambiguity and side lobe level, which reduce the sensitivity and create many false alarm. Of course, if the point cloud density is related to the array size. So if you have if the radar has a small amount of antenna element, then there will be a small amount of points in the image at the end. There are many multipass issues and also calibration issues. So not an easy task at all. If you look, for instance, on SAR, synthetic aperture radar, that also was mentioned in the present talk, the vehicle must move. If the vehicle is static, it doesn't, of course, detect anything, and it's automotive vehicles motion is not regular, so there should be a lot of compute invested in motion estimation and compensation. And last but not least, it's very good looking off bore side, meaning to the side and not to the direction of travel of the car. So it's not good for the front unit, for instance, at least for the kind of the solid angle that is along the driving direction. A third solution could be analog phase array, but then there are issues of accuracy, time on target, but also RF cost. Another solution is not to compromise on the hardware, to generate radar with a large uniform array and use digital implementation. So this is give you the best quality, and then count on silicon technology evolution to compensate or to reduce or to improve the efficiency of the sensor. So with process improvement, there is reduced less power consumption and less area. So the price of the chip is reduced, and the clock frequency of the SoC can or the radar processor can be increased, and by this we can achieve more compute capacity. Also, memories evolve, so we get reduced latency and better access bandwidth. The system interconnect also increase the throughput. For instance, if you look at the internet, even automotive internet, so in the past it was even not 1 gigabit internet, and today people talk about 10 gigabit internet. So there is a very nice evolution also in the interconnect. And of course, integrated AI give the AI advantage. And last but not least, the radar radar architecture has to be built for this approach, so for this strategy, in order to be efficient, because otherwise it can end up to be expensive and consume a lot of power. In the kind of the second half of my talk, let's see how much Vadim, how much do I have?
Yeah, you just go ahead. How much do you need?
No problem. Okay. So I want to present some videos, Mobileye solution, and then some real life examples. Okay, so you can see it in your eyes. So Mobileye BSR product is a software-defined imaging radar. We at Mobileye designed it completely. Some of the chipset and the system and the mechanics and everything. It is a massive MIMO unit with more than 1,500 virtual channel in the front unit and almost 400 in the corner unit. It achieved sub-degree azimuth resolution. We developed the RF ourselves, so it's very sensitive. It has a very low phase noise, which is important to far distance sensitivity, far distance object sensitivity. We developed the antenna array and the algorithm to deal with multipath and side lobe level. We intentionally separated between the receive and the transmit RFICs because of what's called the transmit leakage, meaning that in radar the transmitter and receiver are active simultaneously, and it's required that the TX will not, the transmit will not overwhelm the receiver. So there's a lot of engineering to control this leakage. High sampling bandwidth and wide word length, 20 frames per second with different scan types, and our own radar signal processing that can deliver more than 11 tera operation per second. Okay, now we will start demonstrating. By the way, it's a bit old videos. Today we do even better. But I will start with max range. But before we do that, I will explain the color code. So for statics, green is a low statics, like a bush or a pavement or a low pillar or whatever, and yellow is high, like a tree or something like that, or high building. In moving object, red is closing, meaning coming to us, and blue is departing. So the motorcycle is departing in this case, and it will be blue. You will see that the motorcycle is stably detected until 300 something meters, and then it's a bit flicker until 350. Okay, so you can see the motorcycle. It's almost not visible in the camera, but very, very solid in the radar. You can see a high tree in the left, in 180 meter, and the motorcycle goes on. Now it's flicker a bit. So you can see a very reliable detection of the motorcycle. Now this scan is the urban scene. By the way, the building is our office in Israel. And here we want to demonstrate ultra low azimuth lateral error in presence of reflectors and real scene. So the scene is, as you can see here above, is a person standing near a car, like open or close the door or locking the car. And you will see that as opposed here on the right that where it is, that there is a green actions that are used for the parking car. You will see from 75 meters, you will see the pedestrian. It goes. You will see another pedestrian here, and now you can see it, and you can see another pedestrian crossing, and you can see it as well. This was the short one, so I can play it again if you like. Let's see what's coming next. Okay, this is the tunnel. Tunnel is a difficult scenario also for camera because of the bright kind of end of the tunnel, but also for radar because tunnel consists of lots of concrete and iron is a good reflector. So it's a challenge for radar, both from side lobe level and dynamic range point of view, as well as resolution to detect a car, as you see here. Currently, what you see is this picture. So the upper picture will show the scene evolution, and you will be able to see the parking car, which is here is kind of highlighted as the car approach as the radar approach the tunnel. So now in the upper picture you see the tunnel. Now you can see the car in the middle. There's a zoom in a 50 meter. You can see the car, and so although the tunnel is very has a very high RCS, other cross section, very much higher than the car, than the parking vehicle. It's clearly detected, and you can also get the impression of the issue with camera as the end of the tunnel is very bright. I like this scene very much because it's really justified the term imaging radar. So just enjoy it. You will see the trees. You will see parking cars. Let's see. Also in elevation, not just azimuth. So the scene, although it's a close range here, is clearly seen as an image. Okay. Metal bridge. Metal bridge is again like the tunnel is a very challenging scenario because we'll see here two pedestrians near the bridge. The pedestrian has RCS of let's say -5 or even less than that dBSM, and the bridge could get to 30 or even more than that. So there is at least 30 dB difference here. Let's play it. So you can see the blue pedestrian and also the one on the left. And you can see that the scene is not blocked by the bridge. That the radar as a sensor is not overwhelmed from the metal bridge. Here we have available space, drivable space that is marked on green based on radar alone, of course. The first video is of a highway scene. So we can see that the pavement, the curbstone is clearly detected, all the vehicles. So really you can understand the drive by radar kind of claim. You can see on the right side, it's a kind of top view. And now we move to urban scenario. So you can see the pedestrian walking, the curbstone, the vehicles. So you can see that the radar detects all the objects in the scene. Okay, a second. This is a parking, if you like, or how the radar detects objects that are very close to the vehicle, like almost touching the vehicle, and in a very wide field of view. Here it's 170 degrees, or almost 180 degrees. So it's very, very wide. I mean, the antenna is kind of a planar, so it's really the up to the narrow kind of end of the antenna. And you will see two people. One is going 1 meter away from the vehicle, and then the one that is very, very close to the vehicle, and you can see on the bottom a red marking that present the distance from the vehicle. Okay. So here you can see that the pedestrian is clearly detected in the entire field of view, and now you go very, very close to the vehicle, and also very wide angle. You can see. You don't see it in the camera. The camera is not good as the radar. The radar is much better than the camera. Okay, here's a list of full cargo and hazard and things that you may find on the road. We measure the radar performance always near a guardrail. So it's not an ideal scenario. And today we are even better than this performance, but just to give you an example on the testing that we do. So you can see here that we have digital differential GPS to mark the object, and we have the guardrail, and here you have a sewer kind of opening. So it's not an ideal scenario, it's a real life. And you can see here like a line a man. it could be, you know, a motorcyclist that had an accident or whatever, or someone with a medical concern. So you can see that in this case, it will be detected in 200 meters, but today we already detect it in a longer range. So the person is marked with this yellow square. You can see that it extends beyond the guardrail.
Ophir, I'm not sure I can hear you.
Sorry?
I'm not sure you were audible.
You missed the last one or the entire presentation?
No, just the last one. Okay, please go ahead. Yeah.
Okay, I can replay it, no problem. What I say here is that this is kind of an example with MRR mode. It's not LRR, so it's kind of the typical mode. It's a man lying 1 meter away from the guardrail, and you can see that it's detected in 200 meters, and today we detect it even better. And I said that the man is specified by the yellow square. So I will replay it. So you can start, you see that from even beyond 200 meters, you see it extended beyond the guardrail. And mind you, if it would have been LR, it would be even further away. Okay, it was good now?
Yeah, good. Please go ahead because we're a little bit above time now.
Okay, I think this is I'll go to the summary. So Mobileye as a leader in autonomous driving have to make sure that it has all its need to implement its AV strategy, and imaging radar, automotive imaging radar is a key enabler for consumer ID, and I think you had the opportunity to get the impression of the performance, and as you can guess, the architecture is about dense array, digital radar, and strong processing capabilities. Thank you for the time. I hope it was interesting.
It was very interesting. Thank you so much. I think we are quite, let's say, beyond time. Maybe just only one short question, and then the rest maybe. Ophir, can you see the Q&A window?
Yes. Yes.